Hello, and welcome to my project analysing the jet cryogenic distillation system for separating hydrogen isotopes. Firstly, why do we want to separate these isotopes? Well, it's a way in which we can recycle the fuel used for nuclear fusion. The fuel generally consists of a 50-50 split of deuterium and tritium, which are two isotopes of hydrogen. Once the fusion reaction has occurred, these two isotopes are mixed in with all the other isotopes of hydrogen. Cryogenic distillation is one method for separating back out the deuterium and tritium to be reused. The JET facility is an experimental active gas handling facility which contains a cryogenic distillation system, among other gas processing units. Being an experimental facility, there are opportunities for optimization and improvement, particularly for factors that become more important if the technology was to be scaled up. In particular, I first looked into pre-condensing the column feeds to see the effects on separations and heat duties. I then looked into refrigeration, which could form a large part of the operating costs due to such low operating temperatures. Currently, jet uses helium circulating in copper coils. In the past, there have been shortages of helium, and so I investigated hydrogen as a potential alternative. My aims were to first simulate the jet cryogenic distillation system using Aspen Plus, then investigate the effects of pre-condensing the feed using heat exchangers, and then finally run a simplified refrigeration cycle with both hydrogen and helium to produce a given cooling capacity and compare the input power requirements. Figure 1 and 2 show my Aspen simulations. Figure 3 shows the mass fraction of deuterium and tritium in their respective product streams as the column feed vapor fractions were increased from liquid at bubble point to vapor at dew point. As you can see, tritium remained essentially unchanged, whereas deuterium decreased significantly from around 0.94 to 0.85. Figure 4 shows the effect on reboiler duties. For each column, reboiler duty decreases with increasing feed vapor fraction. Finally, Figure 5 shows a breakdown of the input power requirements for both hydrogen and helium to produce a cooling capacity of 600 watts. Helium had a greater input requirement of around 32 kilowatts, whereas hydrogen only required around 3 kilowatts. So to conclude, there needs to be a compromise between maximizing the mass fraction of deuterium and minimizing the heat duty of the columns. Also, hydrogen may be a better alternative as refrigerant than helium, as it has far lower power requirements. However, the cycle used was simplified and very inefficient. The future work to be done includes adding equilibrators to the simulation of the jet system. These are reactors that promote conversion of some isotopes into deuterium and tritium, and so would increase the mass fraction of these products. There also needs to be an economic analysis applied to the data on pre-condensing the feeds in order to quantify the compromise. Finally, more efficient and commonly used refrigeration cycles should be tested with hydrogen against helium to verify its suitability as an alternative refrigerant. Thank you for listening.